All right, we'll get started. Good afternoon and welcome to today's Richard M. Karp Distinguished Lecture. I'm Sandy Arani. I'm the Associate Director at the Simons Institute. And for those of you who are unfamiliar with the Institute, we are the leading international venue for collaborative research in theoretical computer science, established with a very generous grant from the Simons Foundation. The Institute brings together researchers from all over the world in theoretical computer science and related fields. We established this particular lecture series, the Richard M. Karp Distinguished Lecture Series, to celebrate the role of Simons' founding director, Dick Karp, in establishing the field of theoretical computer science, outlining its foundational problems, and contributing a stunning array of results. This lecture series features visionary leaders in the field and is geared towards a broad scientific audience. So we're very grateful to the people who have contributed to make this series possible. And today I'm very happy to welcome Val Tannen, who's been here throughout the semester. Val's a professor of computer science and information at UPenn and has been one of the organizers of the Logic and Algorithms program in database theory and AI. And indeed, his research interests align perfectly with the program, as he's had a deep interest in the intersection and connection between logic and computer science throughout his career, initially in programming languages and more recently in database theory. He's worked on query language design optimization, more recently models and systems for data sharing, data provenance, managing uncertain information. His work has won numerous awards, notably 2 Test-of-Time Awards, the 20-year Test-of-Time Award for the International Conference on Database Theory, and the 10-year ACM PODS Alberto Mendelzon Test-of-Time Award. So his talk today is titled, is it up there? It's changed. Okay, you... Okay. Well, I'm going to let Val say his own title then, and please join me in welcoming him.
Thank you, Sandy. The title that you advertised, which I supplied, was not one of my better efforts. It was too long and almost part of the abstract. This is, I think, a little more punchy. So I'm going to talk today about things between streaming, recursion, and incremental computation. Now, this is joint work with Mihai Budiu and Leonid Rizic. They were at VMware when they did this work. They now started a company, in fact, to implement this work, Feldera.com, with Frank McSherry, who already started a company called Materialize.io to implement the earliest version of some of the ideas in what I'm going to present, called differential data flow, and with Tej Chajed, who has verified our proofs, and I'm happy to say they're correct. So Mihai and Leonid, in fact, will be here on Thursday at the Industry Day. They will give a talk, and certainly a whole lot of questions that could be asked about what I'm going to talk would be better addressed to them. They certainly could give perhaps better answers. But let me try to do my best with what is in front of you. So DBSP, DB for databases, and SP for signal processing, which is a less obvious connection, is a platform in which we have 4 things that are worth noting. First of all, we have synchronous streaming of collections, and in particular of collection updates. We have recursive computations, which are realized via synchronous streaming, which is perhaps a little unusual. And we have incrementalization, which is a word that I hate so much to type into the slides that I'm going to actually just say incr, but I will spell it out. So when you see this in red, it's incrementalization, and also via synchronous streaming. And it all should work together to provide an algebra that supports program transformations and therefore optimizations, as we are used to using so productively in various parts of computer science. Of all these parts, I think the one about incremental computation is least familiar, and it's worthwhile discussing a little bit. So consider a program, and the input of that program is I, and the output is O. Here is a picture. And now the idea is, if we change the input I, let's say slightly, in other words, instead of I, we have I plus delta I, then the output, of course, also changes, hopefully also slightly, or at least we are interested in those programs in which the output changes also slightly. And the output is O plus delta O. And the idea is that you would like not to recompute O, because you already did, but just to compute this difference, this increment or decrement, whatever it is, delta O, and just update O with it. Where is this useful? Because of course you're going to give me examples of programs in which just a small perturbation in the input changes completely everything they do. But this is useful in databases primarily, but also, for example, in large graph processing or in stream processing, various similar applications. And the idea is that there, I and O are collections of data. And plus, that you have here in the picture, means update. And update specifically means deletion or insertion. In databases, this has been known as incremental maintenance of materialized views. The idea being that if you have a database and you find it useful to materialize a view of it, that is like a smaller database to make certain queries work faster, you have to change the view when the database changes. And that's called incremental maintenance. So it's clearly fitting with that. And what I want you all to remember from this picture, and in the next slide I will elaborate on that, is that what you would like, what's desirable, is for this delta O to actually be computed by some version of the query. Let's call it the increment version of the query Q, that takes the input and just the change delta I. And in a moment, we'll comment why this is desirable. Now, what you just saw, this picture here, I replaced delta O with this Q delta. It's called the delta rule. That's a tradition in databases. And using this kind of delta rules systematically has been a profitable way of understanding how to apply incremental computations in the field of databases. So this picture here says this is the delta rule for some general query Q. And the picture, I just wanted to remind you, is like this. Why is this interesting? Because you want to take advantage that typically, delta I is much smaller than I. Instances of databases can be ginormous, but the updates, one particular update is relatively small. And the output also can be like that. The result of the query can be pretty large, but the change can be actually much smaller. Now, people have, in fact, worked real hard, and in fact, people in this program, present here in the room, to devise clever algorithms for certain classes of queries where you can take advantage of this to actually come up with efficient ways of updating views this way. This work is not about that, but I need to contrast it. This work is actually how to take such contributions that people make and integrate them from a practical perspective. You want to use them in an engine that works with complicated queries, not just simple classes of queries. And I say rich because it sounds good, rich and complex queries. So I'm going to follow these four themes that I just stated. First, I'm going to explain what are stream computations, or rather the kind of stream computations that I consider here. I'm going to talk about recursion, how it's implemented with stream computations. I'm going to talk about incremental computation, and then sort of the culmination would be that if we can show how to optimize incremental recursive circuits with our algebraic approach. What kind of streams do we use? Time is going to be the natural number, so these are discrete sequence of values. Here is one. This is a stream of integers. One, think of it from left to right. 1, -2, 2, whatever. So what is a function? What is a stream? A stream is a function S from natural numbers to some domain of values. In fact, the domain of values that we will be interested in is going to matter a lot. But for the moment, a bit of notation. For various reasons, we write S of t for whatever is in the stream at time t instead of as a function notation. For example, here S of 0 is 1, then you have -2, S of 6 is -1. And we are going to denote, we're going to denote the type of streams with values in A by S sub A. Now, what we will be interested in is streams in which the values are collections and collection updates. So this set of streams that I just defined is going to be mostly used when A forms, in order to describe incremental computation, an abelian commutative group. Abelian means commutative. So this is a general structure, and we'll see that we can get a lot of mileage out of this generality. And to begin with, if the values form an abelian group, the streams do that too. And you can actually lift these operations plus or minus whatever on streams. To make them operations of streams, you do it pointwise. The kind of collections that we will work with are going to be Z sets. And, well, of course, more specifically, Z relations. We're going to define them later. But the point is, they do form abelian groups because of the integer Z, set of integers Z. With these streams, we have stream operators. So a stream operator is simply a function from streams to streams. And it could, for example, take streams of values of type A and produce streams of values of type B. Why not? We are going to take advantage of graphical notation. And maybe that's also inspired by discrete signal processing. So this operator here, Q, it consumes this stream I0, I1, I2, and produces this stream O0, O1, O2. And the point is that the operators we work with are synchronous in the following sense. At time t, the operator consumes IT, that is the value of the input stream at time t, and produces the value at the output stream at time t. And this is important because you can have multiple inputs. You can have operators with multiple inputs, like this one here, and you would like to consume from both the inputs the values at the same time t. And that's what really synchronization comes down to, what we need to work with here. How do we get such operators? Well, the simplest way to have operators on streams is actually to take a function on values and just lift it. So here is f from A to B that lifts to a function notation up arrow f, or map of f. You map it from streams of A to streams of B. So for example, if the input is ABC, the outputs are f of A, f of B, f of C. This is generalized to functions of multiple arguments. So here the inputs are A, B, C, X, Y, Z, but the outputs are G of A of X, G of B of Y, etc. What can we do with operators? Well, the great thing that we learned for a long time, how do we apply algebra to computer science, is we can, in algebra, the easiest way to do what to do is to compose. So we have operator composition. The result is what we call an algebraic circuit. Circuits are ubiquitous in computer science, from the circuits with Boolean that use Boolean operators on Boolean values, to actually circuits, arithmetic circuits, and all kinds of other kinds of circuits. So all algebraic frameworks define circuits. Here is a quick example of what I mean. A, B, C, D, E are operators. When you have such a circuit, it actually graphically is a DAG, a directed acyclic graph. And like every DAG, it has sources and it has sinks. Let's assume for simplicity there's only one sink. It always defines precisely a function from the sources, all the sources, to the sink. But if you write a function like this, it gets you dizzy. It's much better to look at the circuit itself to understand how and what it computes. Now, this has been exploited in various ways. For example, parallel execution kind of lives in this, in a natural way in this framework. And we are going to exploit it, but in a different way. How are we going to use this algebraic framework for optimization? We will use circuit equivalence. And that's, the simplest thing that you can think of. If you compose two operators A and B, you have here the operator B composed that does B, that does A and then B. Here you have the operator that does B and then C. Well, these two circuits are equivalent. So this notion of equivalent, very intuitive, is used to validate optimizations in this platform. We come now with these circuits to the second part of the talk about recursion. We'd like to add recursion, and streaming, synchronous streaming, actually allows us to add recursions in a very interesting way. How do we do that? First, we observe that all the operators of interest are what's called causal. Causal means that an operator only depends on the past and the current present input to compute the current present output. They don't depend on the future inputs. I mean, it's like so obvious that you're wondering, why did I bother to put a slide with this, right? And of course, DBSP uses only causal operators. But there are also some other interesting operators which we will exploit. One of them is called delay. It has this notation Z. I'm going to never say -1, but the reason for this rotation again comes from discrete signal processing. If you know that, that's fine, but I'm not going to use it, that motivation. What it does, though, is very simple to understand. It delays the input by one time unit and produces the output this way. So Z of some input I at time t is equal to 0 at the first moment, and then I of t minus 1. Okay. So one thing to insist is, while I am deliberately using the same notation 0 for simplicity, and this 0 here and this 0 here are not the same 0. This is 0 of the natural numbers. It means the initial time. But this 0 is actually some sort of neutral element among the values. In particular, for collections, this is going to be, say, the empty collection, the empty updates, no updates. I'm just going to use 0 for this notation. So graphically, this is what Z does. It's quite simple. And of course, it's causal, but it's more than causal. This operator is what we call a strictly causal operator. I might say for short, strict. And what is a strictly causal operator? Its output depends only on past inputs. It doesn't depend on the current input. So it doesn't depend on I of t. And of course, not on I of t plus 1 and so on, but it doesn't even depend on I of t. So examples of this delay of these strict operators are z minus 1, or you can compose z minus 1 with itself. They all have this property. And you might say, okay, well, what about others? I don't have a simple definition like z, but I have a way of creating, as it were, an infinite supply of strict operators. Here it is. If f is strict, so it's like z minus 1, and t is causal, and t has actually two arguments, then consider this function. Apologies for the lambda notation. So t of s, you leave s alone, but to alpha, you apply f. And now consider the function that takes alpha to whatever this t returns. So you apply the strict operator to alpha. It turns out this operator is strict itself, strictly causal. and that for each s. So now I can actually produce a whole bunch of strict operators. And you're going to say, why? Well, because that's going to be crucial for the kind of recursion that we will do here. And so the simplest recursion scheme is the following. Every strict operation, every strict operator f has a unique fixed point. That is, there's a unique stream alpha such that alpha is equal to f of alpha. And naturally, we are going to call this fix alpha dot f of alpha. And who is it? it's this one. It's so trivial that it's annoying. At 0, it is some sort of value that f of alpha gives you at 0, which is going to be that 0 that I told you about. And at t plus 1, it's going to be f of alpha of t plus 1, but that has been delayed by 1. So now I can actually compute it in terms of previous values. This is a recurrence, well-defined, because f is strict. It's unique by strong induction. But note how essential is the use of synchrony here. If this would not be a synchronous operation, then we wouldn't be able to do that. What's an example of a fixed point? Well, the fixed point of z is very informative. I'm being facetious. Very informative stream of zeros. So you can say, okay, well, this is useless. What are you doing here? Well, here is what I'm doing. Remember all those other strict operators that I could do, which I can combine an arbitrary causal operator, and I already have an f, which is strictly causal, and I can combine them. And it turns out that now this has a unique fixed point from the previous proposition. Okay. This is a picture that I would like you to keep in mind. And all of a sudden, if I am allowed to somehow go back, we call this a feedback. If I'm allowed to do a feedback and take the output, put it through a delay operator, for example, or some other strict operator, and feed it again into a t, then that has, again, a unique fixed point. So you should think of t as the body of a loop. So the kind of recursion that you see here is more like a recursion in an imperative language, more like a while recursion. Okay. And why do I even call it recursion? Well, let's take a simple example. Take f to be z, and now take t to be the lifted version of a function g that ignores its first argument, and to the second argument, it applies some function f. That's all. Now, no matter what the stream of s is, the result of this circuit is the stream f of 0, f square of 0, f cube of 0, and so on. And if you have a way of sort of collecting all these values, then all of a sudden this looks very familiar, because it looks like what we call a Kleene fixed point in various theoretical corners of databases and programming languages. Right? So I can, in fact, it's already suggesting that I can just use this kind of construction to implement data log. And something that I'll explain later is called a while relational queries. That is, I can repeat relational algebra and keep applying. Okay. The idea actually bears fruit in a surprisingly general way. You can also do mutual recursion. Here is a system of two equations in which you have two operators, T1, T2, which are causal, and two which are strict, F1 and F2, and you just feed them across each other, the outputs as an input to the other one. And that also has a unique fixed point. In fact, you can see this as a corollary of the general theorem you saw before, but you need to use here some kind of construction, which I will not explain, but it's fairly intuitive. You need the product of the T1 and T2 and the product of the F1 and F2, F1, F2, T1, T2, and you also need to swap the two streams that you input. Now, it turns out that this is actually a very productive idea in that we can define now the general concept of a recursive DBSP circuit. What is it? It is an algebraic circuit that we understand, the usual stuff. Plus, I can now, and remember that's a DAG, plus I can now add what we would call a feedback path. So feedback also comes from digital signal processing. You can get things called bistable circuits and stuff like that. What is a feedback path? A feedback path consists of two arrows that sandwich between them a strictly causal operator. So this is not an edge. This is actually a combination of two edges with a strictly causal operator between them. But you can actually insert this between any two nodes of this DAG that you start with. So all of a sudden, soon it's not a DAG anymore. Okay. There's an example here. That was the circuit that we had before, A, B, C, D, E, and I've added a feedback here, and I've added a feedback there. And the proposition that you can state here is that now the circuit with recursion still defines a unique function from sources to sink. This is what Dana Scott calls a proposition that proves itself. And that already gives us, well, you can say, oh, so that's your programming language. Now, of course, this is not a practical programming language, but the way we think about it is as a compilation target for a whole bunch of practical programming languages. Okay. So we have recursion. Now let's define incremental computation, again, with just what we have worked with so far, plus we are going to actually need to be concrete about the values, what the values are. So far, the values could be anything. But now I want the values actually to form an abelian group of z-sets. So what is a z-set? Well, the idea is to generalize. So this is a normal database table, name and age. The idea is to generalize this and to put on every tuple a weight, which is an integer. Now, putting a weight, which is just a natural number, is something that in databases has been experimented with. It's called bag semantics versus set semantics. If you actually put negative values, it turns out that this is just the right formalism for representing updates. So if a tuple has here -1, that means that tuple is deleted. If a tuple has -2, that means that two copies of that tuple are deleted from a bag semantics table. So to be precise, a z-function is a z-set is a function from some type of tuples to z, the integers, that must have finite support. In other words, it must be 0 almost everywhere, except for finitely many tuples where it can be non-zero. And we can do that. We can do sets, we can do bags, we can do sets of updates, and that's already interesting enough. Now, because Z is an abelian group, then point-wise, the C sets also form an abelian group. And as we commented before, the streams of Z sets also form an abelian group. So it's abelian groups everywhere. Because we are in an abelian group, I'm going to also feel free to use the operations of the abelian group because I know what they are. Now, again, using digital signal processing conventions, plus is going to be represented not as a box, but as a circle. And minus also as a circle. Plus is binary. This is the unary minus from the abelian group. So what can we do with this? Well, it turns out that we can do differentiation and integration. You already probably raised an eyebrow where on the first slide where I described the work of my collaborator, previous work, it was called differential data flow and differential data log. What do they mean? Well, let me give you an idea of what they mean. Look at this circuit here. What do we have here? So the input stream goes both into the plus, but it also goes through a delay into the minus. So that means that, well, at the beginning, the output at 0 is the input at 0. But after that, because of the delay, the output is s of t minus s of t minus 1. So some people like to call this the discrete derivative. There's actually a whole bunch of mathematics called discrete derivation and discrete integration and so on. For us, we denote, although it's definable in terms of what we already have, it will be convenient to have a notation for it. We denote it by script D. And it's a circuit that works on strings to strings, where A is some abelian group. That's what I need. And what it is that the output is the stream of changes in the input. So if the input is, for example, 1, 3, 2, 5, of course, I'm not using streams of integers, but this is just for illustration, then the output is 1, 2 comes from 3 minus 1, negative 1 comes from 2 minus 3, 3 comes from 5 minus 2. So this is a stream of changes that happen in the input stream. Dually, we have integration. So look at this circuit. Now, this one is defined with recursion. So without recursion, we couldn't even define it in terms of what exists. So it uses the delay as the feedback in the feedback edge. And it does here, all it does is plus. It's kind of the simplest application of recursion, of that simple recursion scheme. And so what it does, let me just cut to the chase, is that at time t, the output is the sum of all the elements in the input stream from 0 to t. And you can call it discrete integral. So if actually S is a stream of changes, then the output is the original stream. So this is a stream of changes from the previous slide, and this is the original stream from the previous slide. So as probably you have seen already, I and D are inverse to each other. That's going to be one of the essential equivalences that we use in our circuit optimization. And I and D are causal. I have to keep saying all the things I define are causal because I need causality in order to keep defining things further. Okay. So why is this interesting? What do I do with differentiation and with integration to talk about incremental computation? In order to understand that, we have to see databases as a stream of instances. So an instance of a database is the content of a database at a fixed moment in time. You can call it a snapshot, a version. Let's call it an instance. And when you have such a database, of course, databases live permanently to change. Transactions, I mean, not all transactions, but the transactions we have in mind here do updates. They do insertions and deletions. So every transaction, when it commits, makes a change to the database. That means that you can think of a sequence of transactions defining a stream of changes. So I'm going to use a little bit overloading this poor delta also as a symbol for the stream of changes to the database, to the instances of the database. So the delta at time t is the change affected by the transaction at time t, the change to the instance of the database affected by the transaction. Now, if I is a stream of instances, or snapshots or versions, then I of t is the instance of the database at time t, that is the instance of the database after t transactions have been executed. So you can represent this visually in a moment. So you can think of I as the integration of the stream of changes, like this. So this is the stream of changes. I0 is not delta 0. I0 is the original instance of the database. Then a change happens. That's delta 1. It could be an insertion, could be a deletion. Then more changes happen. And the output is the stream of database instances as they evolve through time. Views, because they were mentioned at the beginning, are a very useful concept in databases, a very practical concept, Because sometimes certain queries run faster if you had a certain view of the database used as if it is already in the database. This is part of the database. So people call these things materialized views because they are being computed and the database administrator decides to materialize a certain view. The problem with views is that while they make life easier for certain classes of queries, they also have to be maintained because the database changes, and when the database changes, you have to correspondingly change the views. And that is what's called incremental view maintenance. So here's an example of a view here from that table with age, whatever. There is a query. Every view is defined by a query. So Q of the instance I at time t is equal to the view at time t. So in terms of streams, you can think of the stream of view snapshots, call it V, as the lifting of the query Q applied to the stream of instances, call it I. Here it is. This is the stream of instances incoming here. This is the stream of views outgoing there. So keeping this picture in mind, we can now understand incremental view maintenance as operating, as being affected in a stream-like fashion. So before we look at what's here, let's look at the picture. In the picture, we have the stream of changes, that delta. I0, then the change delta 1, delta 2, delta 3. That's the input of this red dotted box. The output is V0, which is the original view on the original database, and then changes to that view, delta V1, delta V2. So these are the updates to the view. So stream-wise, you would like to map the stream of changes to the database into a stream of changes to the view. And it turns out that this is, in fact, obtained by doing integration, applying the lifted version of Q, and then doing differentiation. I mean, it's very easy to see this is exactly what this does. Again, to relate to the picture on the previous page, previous slide, notice that what flows through this arrow is the stream of instances, and what flows to this arrow is the stream of views. Now, this we call incremental computation, but that's not how incremental computation is implemented, obviously. And it would be pretty stupid to keep creating all the instances and so on. What you want to do is whenever you find in your circuit this sequence of 3 operations, integration, lifted query, differentiation, you want to replace the 3 of them with one box, which we call up arrow Q delta. That is an increment version of Q on streams. And you want to replace it with a customized implementation of that in fact has state. Even if the query itself doesn't have to have state, if you want to do incremental view maintenance efficiently, you need state. People do things like pre-processing of the instance and using clever data structures so that when the updates come, they actually compute the updates to the output efficiently. Okay? And then measure complexity, like can you just, for example, pre-process the instance in linear time, and can you compute the updates in time that's constant, perhaps, or perhaps just linear in the update of the input. And therefore, that's why you need state. So that's the claim that replacing here, this part on the right-hand side, D composed with this, and implementing this in a clever way, performs efficient incremental computation of the view. You may recall Q delta, which is the increment version of the query. The relationship between the two is not visually obvious because they have different numbers of inputs and so on, but it can be made precise. We are going to go further and say, well, why not? Replace incrementalization simply means whenever in your circuit you have this composition, integration followed by some operator followed by differentiation, replace that with Q delta and implement Q delta in a better way. And we can define this for all streaming operators, not just lifted queries. And the reason we do that is because this is going to be used in algebraic manipulations for optimization. Again, I repeat, this is not, you don't implement Q delta like this. It doesn't make sense to implement it like this. You just want to implement it in an optimized fashion, and that's where good algorithmic work is needed. This can be generalized to multiple inputs. This is the incrementalized version of an operator with two inputs and one output. You put the integration on every input. And now I'll put these two together, the recursion and the increment computation, to apply this, to answer this question. How do we apply these delta rules to a recursive circuit, a complex DBSP recursive circuit, one of those that I showed you earlier? Well, it turns out that it's very nice, because now all of a sudden we can actually prove literally algebraically prove that the composition and incrementalization commute. These are called chaining rules. And that incrementalization and fixed point, these are called cycling rules. And this is hard to read, but look at this. So if you do incrementalize a fixed point, here it is, t z minus 1, I and d, well, you can just replace it with t delta here. It turns out that you can have here an arbitrary strict operator, but z to the minus 1 delta, delta is z to the minus 1. So I'm just shoving this under the rug. The point of this is that I made a claim at the beginning. The claim was that recursion and incrementalization play nicely together. I don't know if I made it in these exact words. And so that means that now just repeatedly applying these rules, we can incrementalize a complex recursive circuit by incrementalizing each component independently. And if you have worked on incrementalization of data log, you might appreciate this, because all kinds of complications in the interactions between incrementalization and recursion. The second point that I want to make as an advantage to advertise the advantage of this algebraic platform is for what's called linear queries or bilinear queries. What are these? So if you have types of Z relations A and B, if you have a query that has this property, it's called linear. Okay, that's homomorphism with respect to plus. And there's also something called bilinearity, which just means, as usual, linear in each argument separately. You fix an argument, it's linear in the other. And why are we interested in this? Because it's very common. Projection, selection, group by, well-known operations in databases are linear. For those of us who are fans of nested relations, map, flat map, nest, and nest, also linear. Cartesian product, join, intersection are bilinear. Pairwise is also bilinear. Union is not bilinear, if you think about it for a moment, but you can see it also as linear because it works on, but you have to see it as working on pairs of instances. And people have noted what I'm just telling you here for a good reason, and that's because it simplifies incrementalization. Before you protest, although I don't see anybody protesting, I want to point out that this works for bag semantics and Z-set semantics. It does not work for set semantics. It's just not true. For set semantics, you need to add to your circuits a duplicate elimination operator, a more general one, because it also needs to deal with negative instances, with tuples which have negative multiplicity. But it turns out that this distinct operator, duplicate elimination, can also be incrementalized. Maybe it's not so algebraically elegant, but it can be done, and you can continue to apply incrementalization even when your circuits work on sets. You should also observe now that if a query Q is linear or bilinear, then the corresponding lifted version on streams is also linear and bilinear. So therefore, I want the same thing that you'll see here for streams. But before I show it for streams, let's observe how nicely linear and bilinear queries actually work for incrementalization. So this is before streaming. This is the general rule, but you see for linear queries, this Q delta is just simply Q. You don't need to do anything. No need for clever implementations. On the other hand, for bilinear, and this is really hard to read, it's still simpler than just having to repeat everything. You do not need to apply the operation on both instances, but you do need to combine the instance of one argument with the update on the other, and so on. But this is well known to people who actually have devised algorithms for incrementalization of joints, which is a crucial line of work. I want the same things for stream operators, so we can use it in our context. And for a linear operator, this is now an operator on streams. How nice, Q delta is Q. For a bilinear operator, we didn't know what it was. But it was our algebraic approach that allowed us to discover what it was. And we found that it's this. I know, do not even try to decipher this. But on the next slide, I will have a circuit that does it. That will be easier to read. But I want to point out that we were able to discover this rather complicated implementation of incrementalization for bilinear operators because we were in the right framework. Here it is. So you can prove in our framework that the incrementalized version of a bilinear operator T is actually equal to this circuit. And in this circuit, you have three instances of applying the binary operator T. But if you think about it, it actually does apply only on updates for each of the arguments or on instances and updates. And as before, you do not actually implement integration. You just write it so that you can understand what it does. What you do is you keep state. This is a stateless circuit, but you keep state. Okay. I've subreptitiously added a point here because I didn't want to end with that complicated circuit, which is pithily entitled remarks. So where do we go with that? Oh, I already know where Mihai, Leonid, and Frank go because they founded the companies. They're using the ideas, which again come originally from differential data flow. And where do I go? I don't have any financial interest in their companies. I have only an emotional interest in both of them that they succeed. So take that as you may, but I love this approach. So theoretically, I would like to point out a few things that may guide us in future work, which may also apply practically. Well, typically, query languages in databases are much touted to be declarative. Oh yeah, a database is very nice because you can use declarative programming, which is intended to mean you can say what you want the answer to be rather than saying how you want the answer to be computed. Okay. And of course, that's the purpose of something like logical statements, right? Well, the thing is, stream recursion, this looping, that's not so declarative. I think you will agree with that. But even with this bit of not declarativeness, I think that this platform allows you to mix declarative aspects with non-declarative aspects in an appealing way. Things that happen are interestingly. So you can implement data log in this framework, and we certainly did. the computation for a data log straightforward implementation is what in data log theory is called naive evaluation. It's a computation of the bottom-up fixed point. But if you take the incrementalized version of the circuit, incrementalized the way I've showed you, it turns out that that's the semi-naive evaluation. Okay, now, those of you who are not into databases are making an effort not to laugh. What's with a naive and semi-naive? It's not, these are not terms that I have invented, but they are established. So, I mean, frankly, nothing is naive here. But the naive evaluation just computes the fixed point just by adding facts. The semi-naive evaluation is trying to compute it more efficiently by not adding certain facts again and again and again. Okay, that's good. The other thing that has been a problem is combining negation with recursion. Well-known problem, semantic problem. All kinds of interesting theories have been developed just to make negation and recursion, as I say, play nice with each other. I don't think we've managed. They don't play nice with each other. Well, the thing is that something like collection difference, I can add that operator. In fact, I've already added it. I said every relational algebra operator is in DBSP. Collection difference and stream recursion, it's not a problem. It's just looping. But the way I suggest that we think about it is the following. Look at this. This is a construct that's in the style of procedural languages that does the following. You keep applying relational algebra expressions to some relation variables, and then you assign the results to those relation variables. And you keep doing that while the content of these relation variables change. You are going to laugh, but this was proposed, I think, in 1982 by Chandra and Harel, or 1980. And it's such an obvious thing, but it's not declarative, right? So it has, to my knowledge, it has not been used as a practical database language. But in this framework that I just described, it's a very natural application of recursion. Moreover, the calculations here, they stay in p-space because, you just can't go beyond polynomial space. What may happen, of course, every time you have a while is that may not terminate. Okay. So maybe one lesson is, let's try this. Let's try while languages for databases. The relational algebra is perfectly you can think of it as declarative. It's equivalent to first order logic, which is declarative. So the context in which I make this proposal is a very beautiful context. It's a part of database theory which I love. These are the names of the people who have made the contributions I'm going to list here. The first one is Fokion Kolaitis' contribution, who showed that stratified data log is actually strictly included in various ways of mixing data log with negation. I'm not going to be specific which one you proved, but various ways. Which actually is a result that is underappreciated by the community at large. I've talked to systems people who only understand adding negation to recursion as using stratified data log. And I don't think they know this result. I mean, certainly they knew after I told them, but other things are some monsters called data log negation. This one, you put negation in the rules, but you also put negation on the heads of the rules. I'm not going to try to define it. It's equivalent to first order logic plus some fixed points, but those fixed points can be defined equivalently in inflationary semantics. Inflationary semantics is perfectly well working with this kind of recursion I've showed you, but it's equivalent in expressive power with monotone and positive fixed point and so on. These are called fixed point queries. Then there are these things called the while queries. These ones, You can define them using data log with negation in the rules bodies, but you only take partial fixed points because sometimes it doesn't terminate. Or you do first order logic with partial fixed point. Or you do this while that I just told you about. They're all equivalent. And beautifully, it was shown that fixed point actually captures exactly polynomial time queries, all polynomial time queries on ordered databases, while captures exactly all polynomial space queries on ordered databases. And moreover, even on unordered databases, fixed point is equal to while if and only if p time equal p space. I call this kind of results that circumscribe our research, because we know it's like we are in a box where we know where the edges are. And it's always useful to keep them in mind and think this way. So these last ones are by Vardi, Immerman, Abiteboul-Viano.
Last one, sir.
Abiteboul-Viano, this is Vardi and Immerman. Chandra and Harel, some equivalences here. And that's it. I was surprised that there were no questions during my talk. Usually you guys are a lot more aggressive, but I understand that theoretically speaking, all those propositions, they were self-proving.
I think it's quite a lot. So if you can go back to the slide on Quo Vadis, like 2 slides back.
Quo Vadis, where are you going?
One thing that is that when we talk about data log, usually we think about set semantics. Like data log,
yeah,
with recursive rules.
Yeah, data log with back semantics is may not terminate.
Your whole framework was about Z sets Z relation back semantics. How do you reconcile this?
So the implementation of DBSP implements both set semantics and back semantics. And data log. To my knowledge, it does not implement while queries, in spite of my exhortation. What is there to reconcile? So non-termination is a fact of life for systems people. But it is not a fact of life for theoreticians who always like the idea that everything terminates, and preferably in polynomial time. So from a practical perspective, I don't think there's much to reconcile. From a theoretical perspective, I think that there are a whole bunch of interesting questions about the complexity of incrementalization or incremental evaluations of queries which are even a little more complicated than the classes of queries for which this was done successfully, which have mostly focused on conjunctive queries. Those are quite simple compared to some of the queries that I have thrown at you here. So yes, there's a whole bunch of results there. And it's possible, I think, that we might be able to use this kind of representation in circuits as a way of understanding the incrementalization of more complicated queries. Not done. But this is a Quo Vadis. Okay. Sorry. Yeah, you have a follow-up?
No.
Yeah.
Val, just a comment. While you said it is procedural and it is, but as you said in the next slide, it's also partial fixed point logic, which is declarative.
Yes.
So in some sense, it is declarative.
Well, I mean, so partial fixed point is a fixed point. The fixed point part is declarative. I don't know if the partial part is declarative because I don't think one understands non-termination in a declarative manner.
Like the system of recursive equations. That's
Yes.
what I mean as declarative. Okay?
So every optimization that can be done at the system of recursive equations, that's beautiful. That is declarative.
Now, I have another kind of broader question. You spent, I don't know, 15 years advocating for the importance of semi-rings.
And here I am with abelian groups.
You throw out all by putting the abelian groups, which again you can handle. I understand you can handle updates, and you need it for the integration, right? Differentiation. Right?
Yes.
But what happened to all these beautiful semi-rings that are so important in provenance? Your polynomial semi-rings.
I mean, so
The fuzzy semi-ring.
okay. Nothing prevents us from trying to consider provenance even for this language. I mean, just the fact that we have a notion of looping,
Considering provenance, I'm saying,
considering, and the provenance that we would consider would be
what do you do with the relations over these semi-rings, which are not rings?
I mean, the updates are naturally, I mean, when you cannot talk about deletion without this. Now, as you also might know, Erich Redl and I have done some work where we actually talk about deletion and insertion in a dual way. And from a provenance perspective, you can represent this with different kind of abstract tokens, negative and positive, yes? It's possible that we can marry the two, and it's one of the things I think I would like to do, but I don't see an immediate connection. So associating, so just like we have systems of equations in which we will have updates, when you do partial fixed point, you also, like in data log negation, you also have some kind of, in those systems of equations, you have some kind of subtraction as well. So I think that that's also approachable. I haven't done it. I don't know how it works.
What is the meaning of partial fixed point?
It just means that you do the fixed point, and if you terminate, congratulations, and if you don't terminate,
You return a default value. Either you reach a fixed point and you stop, or you return a default value. But you detect this is space.
I see. So this is not partial fixed point unless we...
this one is the while is the simplest. The while is for computer scientists, I suppose, the simplest way of understanding. The other ones, which are equivalent, here. So while is equivalent with, let's say, first order logic plus partial fixed point. So here, what do I mean? That you just add LFP and GFP, for example, to first order logic, right? But the semantics of it is not neither monotone nor inflationary. It is what it is. You keep iterating, and if that predicate does not terminate, you don't have a meaning for that.
It's the syntax. You allow first.
It's syntax. That's right. Yes.
So does your framework provide any guidance or suggestions about the efficient implementation of incrementalized components?
Yes. So some of those are some very clever algorithmic ideas involving, for example, transforming the instance or using the instance to create some data structures in which you can represent the updates in an efficient way and so on. But if you look at the class of queries for which those proposals work, it's still a limited class of queries. And of course, people would like to apply it to more general queries. For example, data log, or even, recursion of conjunctive queries or something like that. And we don't quite know how to do that, but maybe this can help. Stein is going to work on that, right?
Okay.
Thank you, Val.